Hello everyone, thank you for visiting my channel. Actually, this is my first video for my practicing method. So today I want to present to you about reviewing international journal. The title is Numerical Study of Natural Convection in a Liquified Natural Gas Tank. This is actually my coursework from Advanced Heat Transfer course at my master degree study. Okay, here we go. We directly go to the topic. Before we start, I apologize to you because this is this presentation I make at my office and pretty noisy here. So just enjoy and hopefully well informed to you. Okay, here we go again. Liquefied natural gas, or usually abbreviated with LNG. LNG or liquefied natural gas is natural gas in liquid form. The process required to convert from the gas form to liquid form is using very low temperature. Usually the temperature down to 80 degrees Celsius to minus 100 degrees Celsius. LNG has very high volumetric ratio compared to natural gas in gas form at atmospheric pressure and ambient temperature. It's around 1/600 volumetric ratio. So, for example, we have 1 cubic meter LNG. It's same with 600 cubic meter natural gas in gas form. So it's pretty efficient for deliver natural gas from one place to another place. Most of time, LNG stays in the storage tank, even in delivery process. There are two common types of LNG tank. First one is flat bottom tank that usually possess large capacity. And second one is VIT or vacuum insulated tank that is pressurized tank around 2 bar, though its capacity is restrained small. The main issue of the tank is BOG. BOG or boil off gas is LNG that changes into gas form due to heat leaks from outside of tank. Its consequences, safety risk at the facility and of course the financial loss. Thus, the objective is to investigate the change of temperature of LNG in the storage tank. Why does the change of LNG temperature become important? Because it is as main parameter that affect LNG change into gas form once again. The type of tank that will be analyzed here is flat bottom tank, but in small size. So it works at atmospheric pressure. There are several symbols here. First one like TA refers to ambient temperature, HA refers to ambient air convection coefficient, and there is fan, of course, for vapor canal, and then there is two form of fluid. First one is liquid, and second one is vapor. Capital HT refers to height of tank, and capital WT is refers to uh, width of tank. There are several boundaries conditions here. First one, the analysis is conducted as two-dimensional flow, horizontal x-axis and vertical y-axis. The initial condition, the liquid form remains underneath, whereas the vapor or BOG is at the top. And then the second boundary condition is all of properties are constant except density. And the third is the density variation attributed to temperature is described by the Bose-Einstein approximation. I personally have a comment about that. Perhaps it is better explained to us in the paper the main reason why it used the approximation. Since there are other approximation as well. And then the fourth boundary condition is the liquid vapor interface remains stationary. And the last one is methane at 1 atm or atmospheric pressure, and the saturated temperature is 113.36. Okay, I'm sorry for a little disturbance before. And then we continue to several settings of the CFD software. The author used Fluent 6.3.2. For a little brief, if you are not familiar yet with CFD, CFD is an abbreviation of computational fluid dynamics. It is branch of fluid mechanics that use numerical analysis and data structures to analyze and solve problems that involve fluid flows. Okay, clear enough? Maybe for shorter version, CFD is kind of method to solve fluid mechanic problem numerically based on parameters defined by user. Okay, we go back to the slide. It starts to define the numerical scheme first. First setup is the turbulent model is set with K epsilon model. And second setup is the logarithmic wall function is used at the side of the bottom walls. And the last one is convergence criteria of the iterative solution, set as energy equation uses 10 power minus 7, and other conservation equation is used 10 power minus 5. Once again, I think it needs further explanation why these parameters are chosen. Although in the ANSYS user manual, it has pretty comprehensive explanation. However, it will be much easier to us to understand if it is explained here as well. Okay, after that, the solver scheme is required to be defined as well. The first one is semi-implicit method for pressure linked equation consistent pressure velocity coupling algorithm in order to be convergent quickly. I don't really understand as well. And then the second one is pressure staggering option scheme, more effective for solving high Rayleigh number natural convection. And the last one is a second order upwind scheme for the convection term. Yeah, it's my personal opinion. Of course, it needs further explanation of it. So maybe another slide, I will insert the explanation. The result is as follows. The Bayesian computations are performed by using two-grid system with 8,450 cells using 0.2 mm size and 11,476 cells using 0.1 mm. It is used to determine an appropriate mesh size for the computation. Fine meshes are used in the thin boundary layers near the side and bottom walls, as well as in the liquid vapor interface, whereas coarse mesh for the center of tank is to save computational time. The velocity and temperature fields show no significant differences by using different size of mesh. Those are good mesh size. We could observe the heated fluid phenomenon by paying attention at temperature profile and change of direction of the fluid. It moves upward along the bottom and side walls because of the buoyancy force pulling the lighter fluid up. And then the fluid is cooled near the liquid vapor interface and move downward. The movement of the fluid creates a kind of vortex in counterclockwise direction. We also could see the maximum temperature of fluid is 115.38 Kelvin, 39 Kelvin, I'm sorry. It means small part of fluid in superheat phase or change into vapor phase. Therefore, the BOG generation is occurred. In this section, the simulation is conducted using three different values of ambient air convection coefficient using 0.2, 1.0, and 5.0 watt per meter square Kelvin, respectively. And then the heat from simulation is compared to experimental result with the same parameter. My personal comment is I think necessary to be explained how to manage the ambient air convection coefficient, science that cannot be obtained by direct measurement. The author shows us that the results between simulation experiment are almost the same, about 99% accuracy in average. I just still wonder how to manage the ambient air in order to have a curtain of value exactly, which the result will be compared to simulation result later. However, anyway, the result the results show to us that the set parameters for simulation are valid because it has very similar result compared to experimental one. For the next section, analysis will be conducted with various tank size. S length means access ratio covering the width and height. For instance, S length 2 means the width and height become bigger twice of initial size. The simulation uses three different values of S length, 1, 2, and 4. We could see very similar results as well from the graph. The lines are coincided each other. The vertical line is Q per HA or heat per convection coefficient. That parameter represents to delta T or temperature difference, that very important parameter that determine the pace of natural gas, whether remains liquid or vapor phase. After that, the analysis aims to observe the effect of tank aspect ratio. Tank aspect ratio is comparison between width and height of tank. It is used two different values, 1 and 4. From the Q per HA graph, we could see that the green line or tank aspect ratio with 4 value has lower value compared to red line, initial aspect ratio of 1. It means bigger aspect ratio makes smaller temperature difference. My personal opinion, perhaps it is good for tank manufacturer and LNG industries to adopt this tank aspect ratio. However, I think it requires a further analysis to obtain the limit aspect ratio. My hypothesis is that it must be an optimal value of tank aspect ratio. It is likely impossible if unlimitedly tank aspect ratio will keep the different temperature remaining lower and lower. Since it just used two different value, like I presume, it will be better using more various tank aspect ratio. In this work, unlike rectangular cross-section before, two tank geometries with circular cross-section are tested. The liquid height is different. The first one using H equal with R and the other using H equal with 1.5 R. However, the total liquid is kept constant, both of them. So it causes differences of the radius 0.798 and 0.628 respectively. We could glimpse at border of the tank. Bold border line means liquid area, whilst the dotted line is a vapor area. The boundary conditions are similar with the previous one. And this is the result. The kind of vortex phenomenon is occurred as well, similar with the previous. The liquid is moving upward and downward after we cooled, like shown at middle picture. Then we could pay attention to the graph. The red line, H equal with R, has slightly lower Q per HA ratio compared to the green one. It means the H equal with R tank is able to keep the temperature lower than H equal with 1.5 R tank. Or in other words, H equal with R tank has a better performance than H equal with 1.5 R tank. If we make further comparison, the both value of Q per HA ratio are smaller than the ratio of rectangular cross-section tank in average, like in previous slides. So that means a circular cross-section tank could reduce the BOG generation rate better than a rectangular one. The conclusion of this work is as follows. The first one, the interfacial heat rate is linearly proportional to the external heat transfer coefficient. The second one, the interfacial heat transfer and the BOG generation rate strongly depend on the liquid-solid contact area, but are independent of the liquid-vapor interface area. And the last one, a tank geometry with a semicircular cross-section is found to reduce the interfacial heat transfer rate and the BOG generation rate effectively. This is the reference I use here. The title is Numerical Study of Natural Convection in a Liquified Natural Gas Tank, arranged by Sangeun and Son from School of Mechanic Engineering, Sogang University, Seoul, Korea. Okay, thank you for watching. Don't forget to like, comment, and subscribe my channel. Ya, walaupun medok, yang penting English. Matur suwun. Thank you.